In this video, we're going to discuss how we deal with calculations that involve both phase change and temperature change. So right now, you know how to deal with temperature change. Q equals mc delta T, which describes any point where adding heat is changing your temperature. So you could figure out how much heat is involved in any temperature change. You also know how to use heat of fusion or heat of vaporization to figure out the amount of heat involved in a phase change. But what happens if we need to combine those two? So for example, we may want to calculate the amount of heat required to heat 50 grams of water from negative 10 degrees Celsius to 30 degrees Celsius. So if we keep in mind that the freezing point, melting point of water is 0 degrees, we can see that we are passing that we're starting below the freezing point of water in this problem and we're ending up above it. So if we think about this in terms of the graph, we are starting out as a solid, we are ending up as a liquid. So we really need to do three different things in this problem. We first need to heat our solid up until it reaches the melting point. Then we need to melt it. And then we need to heat the liquid up to the final temperature described in the problem. So we know how to do all of these things. It's just a matter of putting it all together. But essentially, you're calculating three different Q values. Oops, didn't want to delete that one. That there is an amount of heat required to heat the solid up to the melting point, and we can calculate that. So we'll get a Q value for this area. We'll call that Q1. So this amount of heat is the amount of heat it takes to get from negative 10 up to the melting point. There is an amount of heat required to melt our substance. Oops, wrong writing utensil. That we can calculate using the heat of fusion. And then there is an amount of heat required to take the temperature from the melting point up to the final temperature that was listed in the problem. So essentially we have to break this out into three separate parts, three separate equations in order to solve this. So if we think about splitting this up into sort of three different parts, there are three things that we need to do. The first thing is that we need to heat up our solid. We need to increase the temperature of the ice from the starting temperature, which was negative 10 degrees Celsius, to the melting point, which is 0 degrees Celsius. The melting and boiling point of water, I would expect you to know as 0 degrees for melting, 100 degrees for boiling, since those are part of the definition of the Celsius temperature scale. Any other melting or boiling points I would give you in the problem, so you don't need to worry about needing anything else. So we heat the solid first from negative 10 up until the melting point. Then once we reach the melting point, our substance is going to melt. And once it is fully melted, we'll be heating the resulting liquid from the melting point to the final temperature, which was given as 30 degrees Celsius. So anytime that you are changing the temperature is a Q equals mc delta T. So we'll be using that relationship for steps 1 and 3, because that is where our temperature is changing. And then for the melting process itself is where we need to use the heat of fusion. So we're given the heat of fusion in the problem in joules per gram. So to find the heat transfer down here, we just need to take the heat of fusion and multiply that times the mass of our sample. Once we have those three individual Q values, so this was Q1, Q2, and Q3, the final answer is to just add them all together. That Q1 is this distance here, Q2 is this distance here, Q3 is this distance here. What we're looking to solve for is this total amount of heat for this entire process of going from -10 to +30, which involves melting along the way. So to solve this problem, we just need to think about what do we know, what do we not know. So we're looking for all of these different Qs, which means we must have all of the other information that we need. So steps 1 and 3 here are the most familiar, are Q equals MC delta T, which we've been doing for a little while now. So we're looking for Q in both cases. So we need to know the mass, the specific heat, and the temperature change that's happening for the solid. So it's important to keep in mind what state of matter you're in at what temperatures, because that's what's going to give you delta T and the specific heat changes with phase as well. So solid water has a different specific heat value than liquid water. So since we're in the solid state, we're going to take the solid specific heat as 2.04 joules per gram degree Celsius. The temperature range at which we are solid is -10 to 0. Remember, always doing final minus initial. Delta T is going to be 0 degrees minus -10 degrees, which gets us a change in temperature of +10 degrees Celsius. And the mass was given to us in the problem as 50 grams. So that's going to stay constant throughout. It's 50 grams of water that we're heating the entire time. So solving for Q1 here is just a matter of plugging all of those things in once we recognize what numbers we need. So in heating up the water from -10 to 0 degrees, we find that we would need to put in 1020 joules in order to do that. So we're going to need this number later. We'll come back to it. I'm actually going to do step 3 next just because it's really similar. So we're once again doing an MC delta T. Our mass is still 50 grams. Our specific heat is now the one for liquid water, which is the one that probably sounds familiar by now, 4.184. Delta T is going to be the temperature range over which we are a liquid. So this is from our melting point up to our final temperature. So our final temperature was 30 degrees Celsius. We started out as a liquid at 0 at our melting point. So delta T is +30 degrees Celsius. So we can plug those values in. We've got 50 grams, 4.184 joules per gram degree Celsius times 30 degrees Celsius gets us a value for Q3 of 6,276 joules. So those are the more familiar calculations to us. The melting process itself is still a little bit new and different, but not too complicated. The heat of fusion is given in the problem as 334 joules per gram. That means every gram of water requires an input of 334 joules of heat to convert it from a solid to a liquid without changing its temperature at all. The mass of our sample throughout the entire problem is 50 grams. So all we need to do here is take our heat of fusion, 334, oops, too many threes, 334 joules per gram, and multiply by the mass in grams, which gets us a value of 16,700 joules. So then the last step in this process is to just add all of those things together. So the total amount of heat involved in this is just going to be the sum of all of the different parts of Q1 plus Q2 plus Q3. So for Q1, we had 1020 joules. For Q2, we had 16,700. For Q3, we had 6276. So this gets us around 24,000 joules of heat required to complete this process. And when we round that to the correct number of significant digits, the only way to express that correctly is to use scientific notation. So to express this to 3 significant digits, which was how the data was given to us in the problem, we would need to write it as 2.40 times 10 to the 4th joules.